welcome to the weekly colloquium of the School of Astrophysics. We are glad to have Dr. Ognibhor Raychaudhuri as our speaker today. So Ognibhor did his bachelor's and master's from the physics department of Presidency University, and then he went to University of Maryland in Baltimore County for his PhD. After finishing in 2020, he went to the Space Telescope Science Institute for a postdoc. And right now he is back from that postdoc and is going to join the National Center for Radio Astrophysics in Pune, India. So Ognibhor did his bachelor's from 2016 department. He was one of the 4 students in the first astrophysics elective course that was offered at Presidency University. And 3 out of 4 of those students went on to join PhD programs in astrophysics, the other in PhD program in physics, and one of them finished his PhD in 2021 and 21 or 2, and gave the first ever School of Astrophysics colloquium. His name is Shashwat Ganguly, and then Ognibhor is the second one from that batch who is giving a colloquium. The third one is finishing up his PhD now, so maybe sometime later you'll get to hear from him. So, as I was telling the Intro to Astro class, that when humans first started making radio signals, those radio signals went out into space, and maybe some alien civilization will take it someday. But those were the first radio signals that from the Earth, from the humans, went out into the world. So Ognibhor is among the students who were the first signals from the current astrophysics, sort of group of Presidency who went out into the world. So, so we hope that he will give a good signal about us. So no further delay. As there is a program on Jivanananda from 3:30 in the PCM, so I told him to finish early. But anyway, they will start maybe half an hour later. So without further delay, Ognibhor.
First of all, I'd like to thank Professor Ritoban Chatterjee for the kind introduction, and it's an honor to be here. I mean, this is in the School of Astrophysics, but previously, during my days in Presidency, we used to hear a lot of Wednesday colloquia at the PLT2 many a time. So it was always as such a subconscious dream that someday I would be coming back and maybe sharing what I do with the students here. So that's great. And today, essentially, the idea is that I'll be talking a bit about my research and try to tailor it so that everyone gets certain outputs out of it. So since I don't have much time, so the essential idea is that you have extragalactic jets. So my talk will focus on unveiling the physical nature of extragalactic jets, and thereafter try to walk you through, as in if you have a big research problem, what you ask, how you ask, and how you answer in an ever-evolving field like this. All right. So just a very quick introduction. So as far as the big picture goes, I think you have listened to previous talks before, as the fact that you have certain things called active galactic nuclei, which are essentially accreting supermassive black holes. So in these accreting supermassive black holes, in some cases, in a fraction of them, you see this phenomenon called jets. So what are jets? Jets are essentially bipolar collimated outflows of plasma, which basically means beams of plasma directed in 2 opposite directions from the center of the galaxy, or essentially from around the supermassive black hole. So these travel extremely fast, as in extremely close to the speed of light. Gamma can be from 5, 10, 100 or something like that. And the size is also amazing. They range from very close to the black hole, as in microparsecs, to even megaparsecs, which basically means beyond the galaxy, or the host galaxy from where the jet is being launched. So essentially, I would say 10 orders of magnitude in length scale they span. And they are bright in various wavelengths due to high energy electrons guiding in strong magnetic fields. Just to give you an example, so just to give you a general picture of how jets look like. So this is the jet of M87, which is a very famous galaxy. And as I think you have seen this picture much over the last few years. This is the famous picture of the black hole shadow of this jet of this M87 galaxy. So the idea is that if you have a perfect telescope which can zoom in as much as you want and zoom out as much as you want. So if you just observe a specific source, let's say M87, the galaxy here, through various lens scales. So you have zoomed in as much as you can with your ability of the telescope. What you see is basically this black hole shadow. Now, as you keep zooming out, so you see the black hole shadow of M87 here. So as you keep zooming out, you see that jets are beginning to be visible. So it basically means that this is essentially emission in a specific wavelength. So these are all radio images. So this is most likely around 5 to 10 gigahertz and something, maybe between 5 gigahertz to 40 gigahertz, essentially in the radio. So the idea is that you decrease the resolution of your telescope and you keep zooming out so as to see larger and larger scales, probing larger and larger scales. And what becomes evident is that you see these jets as you keep zooming out on a larger and larger scale. So this is around 0.005 parsecs. And as you keep zooming out, you see their entire range, essentially explaining what I said here before. They have this span an extremely large range in order of magnitude of size. So this is really interesting. So all of these, this entire picture can be categorized into essentially 3 parts. So first is the launching region, how the jet is launched, something as powerful as jets, how they are launched from near the black hole. The part where you have the transport, as the energy is released near the black hole, transported through all these distances from 5 milliparsecs, 25 kiloparsecs, for example. And this is the part where the jet ends. Finally, it runs out of energy. It slows down. It deposits its energy in the intergalactic medium. And that's where the jet dies. So jet is born here. It lives its life, and then it dies here. The focus of this talk, I'll just try to focus on the transport mechanisms mostly, and try to tell you how jets work and what we have known more over the last few years based on research in this area. Just another quick slide. I'll just go over this very quickly. So this is again the jet of M87. Just to tell you that these jets are, so the jet of M87 is bright through various wavelengths. So this part is essentially the radio, where you see this again, the black hole shadow. You keep zooming out, see the jet again. One thing to note here, you see that the jet is one-sided. I said that the jet must be bipolar, which basically means it should be directed in 2 opposite directions. But the thing is, these jets are not always perfectly perpendicular to our line of sight. What can happen is it can basically move towards you. And because of that, and since they are relativistic, one part of the jet is highly beamed or is highly boosted, or the flux or luminosity is much larger than the part that is receding away from us, which basically makes this part brighter. And this part is basically dim, and you don't see it because it goes below the sensitivity of your telescope. So this is the radio or essentially radio sub-millimeter observations. And what you see here is the parsec scale jet. So this dynamics here will be different from the kiloparsec scale jet, which is probed by different telescopes. And this is with the Swift XRT telescope, and you have HST optical images. They have various resolutions, and you have different wavelengths. So, and here you have the X-rays, and you have the gamma ray observations here. So as you can see that the resolutions will of course change with different observing frequencies. So essentially the structure of the jet you observe will be different. And that's exactly what you see here. So in this part, we don't have good resolution. So what you see is just a blob, which is the total emission from this entire object. Again, I'll go quickly over this, just as I said before. So you have, let's say you have a jet that you have pi by 2, which is basically perpendicular to line of sight. You see both of them together. But as you now rotate the jet towards you, you start looking at one part, other part becomes foreshortened as well and goes below the sensitivity of your telescope. And you even make it shorter, make the viewing angle shorter than 95 to 45, and even less than 5 degrees, where you just see a point, essentially a blob, which is basically, if it's just directed towards you, you must not see any jet or extended structure. So, and this is basically has to do with the resolution as well as the frequency of observation. And this thing here, just wanted to tell you exactly, if you just put it in your head, Doppler factor is given by this, which is basically gamma is your Lorentz factor, and beta is basically your speed. And your observed flux will basically be given by this delta of delta to the power 3 plus alpha. Alpha is your spectral index. Essentially, the idea is that because of relativistic beaming, the flux will be boosted by orders of magnitude given by as a function of delta. All right, so this is the essential idea of observing jets. So this mostly covers the idea that you might have telescopes to various resolutions and for various observing frequencies. And depending on your telescope, you will see the structure of the jet. You can't see the entire jet in total because you don't have one telescope that can do everything. So the idea is that for various telescopes with various resolutions, you use them so as to see different parts of the jet. Something zoomed in. If you're interested in the structure that is close to the black hole, you use a telescope with very high resolution, very good resolution. And if you want to look at the large scale structure, or which is basically kiloparsecs or even more than that, what you therefore do is use some telescope that has much worse resolution, and you take a look at the large scale properties of the jet. So using a set of telescopes, you should ideally be able to see the jet, say a specific jet, let's say, to its entire lifetime, basically near its launching region to where it is basically terminated. So that should give you an entire picture of a specific source if you're interested in. All right, so now coming to the big open questions, as in what to ask as far as jets go. So in this case, the thing is, we have been studying jets for some time now, but still we have a number of open questions that need answers. So how is a jet accelerated? So the idea is that you start the jet in the launching region, but then it goes through the entire spanning like millions of light years, and then it ends at the intergalactic medium. So how does it happen? So how exactly does it happen? So how does energy transport take place, and how is a jet accelerated from its birth until its death? So this is slightly different from jet launching. Jet launching basically refers to accelerating the jet near the black hole, but then in order to carry it forward, you need something more. This is another open question which I'll not delve into today, maybe. So the idea is that why are many kiloparsec scale jets bright in the X-rays? So there are many open questions related to multi-wavelength spectra of these jets in the larger scales. Something more, I guess, understandable would be what is the nature of these knots. So what I mean by knots are these jets. For example, if you have an 87 here and you have Cygnus A, these are very popular jets. What you see is not a smooth structure. You can clearly see multiple bright blobs of light, multiple bright compact light, spots of light, and you have some diffuse emission here as well. So how is this structure in place? So what caused this? What created this kind of structure? And what exactly are these bright spots of light here? And how is it different from parts that are not that bright enough? And same goes for, let's say, Cygnus A. So these are just observations, since we just observe the light from these jets. So we don't have a direct idea of what's actually going on in the fluid of these jets, for example. So in order to do that, you need to take observations and then analyze them accordingly, which I'll basically show right now, how you do it. So the importance of jet speed, which is basically, most of the focus of my talk today, is that with jet speeds, with measuring the jet speed, you can do a number of things. Basically answer these open questions to a certain degree. So the first thing, as I said before about the idea of jet acceleration. So when you say jet acceleration, that is the question I have asked. But how do you ask that question now? What is specific about that question? The specific question in that case is basically trying to understand. Yeah. It's essentially to understand how the jet Lorentz factor is changing at the distance from the black hole along the jet. So basically measuring the speed of the jet, let's say from parsec scales to kiloparsec scales. So the idea, therefore, you can clearly understand is that to understand properties of the parsec scale, you need one telescope. To understand properties of the kiloparsec scale, you need another telescope. So ideally, you need to combine observations from various telescopes, which probe the entire length scales of this jet, so as to get an observation of the speed of the jet. The energy content of the jet, or also we can talk about the jet power, it is highly sensitive to this bulk Lorentz factor as well. I might talk about it sometime later, but that is also something really important, which we are not very sure about. And lastly, jet emission. So gamma is a very important parameter for relativistic beam, as I just shared before. So the spectrum will be extremely modified by changes in this gamma here. So it goes in all of these radiative processes, which include the synchrotron and inverse complex processes, which basically result in this multi-wavelength broadband emission spectrum for these jets. So understand the speed of the jet at various length scales is extremely important to unraveling their physical nature. So just to tell you, how do we measure the speed now? So we have asked what we have to ask, and how do we answer this question? So this is a slide I'll just spend some time on. So the thing is, what can we learn from measuring proper motions in jets? So when I say proper motions, what I mean is something like this. If you focus on the figure on the right here first. So this is a VLBI observed jet, which basically means that the scale of this jet is only few parsecs. So this is a very zoomed in observation of a jet, parsec scale jet. So the idea is that you observe it, observe the jet, and see how it changes its structure over time. So now it's no more a static observation. We are talking about kinematics here. So the idea is that, so here you see this bright structure, which is the center here. That is your base of the jet, or the part that is unresolved, that is your near the black hole. And here what you see is the knot, a knot which is present at these parsec scales. So this is a static picture, image taken in 2009.42. So now if you have an animation of this, basically telling you how this structure evolves in time, I'll just click on the animation here. What you see is this thing seems to move away. And you see another one that is ejected from this. So there are knots or shock waves, which I'll talk about in a moment. So these knots are ejected away from the base of the jet. I'll just play the animation again. So you can see the time evolving, 2009 to 2011 already. So the idea is that if you look at these knots, if you look at a specific component, this is one specific component that we are tracking over time. So the idea is that to just use your observations and just see how the position of this component evolves as a function of time with respect to the core, you would be able to get a speed, right? So let's say this distance, it was somewhere here before, now it has increased to this, for example, here. So from that, you can get a speed, just getting the distance divided by the time. Interestingly, or strangely rather, what you get is for this jet is that the maximum speed that is reached by this jet or this knot here is 18.8 times the speed of light. You might wonder how that is happening, right? So it is much larger than the speed of light. That's not possible. So what might be happening? So the interesting thing is, so this is a phenomenon that was predicted originally years ago by Martin Rees. So the idea is that the jet is not aligned. Jet is not exactly perpendicular to a line of sight. Jet is not like this. The jet is like this. It's moving towards you. So what happens there is that these knots, let's say, it launches a pulse of light when it is at 2009.42. That is basically the first time where it was launching a pulse of light. So the thing is, by the time it launches another pulse of light, it has already come towards you to a certain degree. So it's basically shortening the time between two pulses. It's some sort of a Doppler effect in this scenario, in which case the frequency of light is not changing, but just the frequency at which you receive the pulses is increasing because the jet is coming towards you. So that boosts the speed. And if you look at this expression here, it should be if you look at this expression here, beta apparent is equal to beta sine theta by 1 minus beta cos theta. So this factor is basically because of the jet that is shorted. You see a component of this jet along the plane of the sky. And this is basically because of the time that is shortened here. So this dominates over this to give you a larger speed. And if you plot it as a function of the viewing angle, what you see is you can reach speeds as much as you want if your this speed is much higher, extremely close to the speed of light.
Boost,
yes.
B by C. No.
No, yeah, beta is B by C. Yeah, beta is B by C. Yes, so the thing is that now if you measure this apparent speed, that is we're calling it apparent, as you can understand, because it's not exactly real, because it's just an optical phenomenon. So the idea is if you measure this apparent speed, you can put some bounds on the underlying bulk occurrence factor and the viewing angle, because you need at least some degree of, let's say, given a specific observation, let's say beta apparent equal to 10, you need some degree of speed so as to reach that, and you need the jet to be at least aligned less than some angle. So this basically goes into the math there. I'm not going into the details here. So the essential idea is that if you measure the speed, you should be able to have a basic constraint on the speed and the viewing angle of the jet.
And R is what? The radius of the.
No, R is the jet counter jet ratio.
And that goes like a power law, which is 3 plus.
Yes, because of the delta to the power 3 plus
Right.
alpha thing previous. Yes. Yeah. And your delta is plus and minus because it's of the receding jet and the counter jet there. All right, so this is basically, when I say Mojave, it's basically a big project that was dedicated to measuring the proper motions of many quasar jets, or basically AGN jets, in the parsec scales, essentially trying to get the speed and dynamics of jets at these small scales close to the black hole. So just again, I'll just go quickly over this slide. So this is a summary of the Mojave program, which has been going on for Mojave monitoring program, which is going on for more than 20 years, few decades now. So this is a plot of the maximum apparent jet speed for the entire sample versus the redshift of the observation. So as you can see, you see a large interesting distribution of as it starts from very low apparent speeds to even much higher. And this part is empty because at larger redshifts, since at larger redshift you don't have that much resolution. What you see is basically probing larger scales. So in those cases, you don't have the resolution to probe small speeds. What you see is a small movement will imply a lot of distance. So in that case, if the jet is not fast enough, you will not see it, which basically makes this part empty here. So they had a sample size of 500 or something like that jet. So it has been fantastic what they have done over last few decades, and it's still going on. But sadly, the program left the field.
Who was the PR?
Matthew Lister.
Oh, Matt Lister.
Yeah, and so this is again a plot of the same apparent speed. Now this is versus the mean projected distance from the core. The primary takeaway from this plot is that what you're tending to see here, it seems like as you go far and far away, the speeds tend to increase, and there is some sort of a correlated increase towards larger distance. But what I'm going to get, from this slide here is that so speeds on the small scales have been measured. So now, which basically means that we know the gamma. If you go back to our goal, that we want to measure the speed as a function of distance along the jet, we have an understanding of the small scale speeds because of this project already. What we don't have an understanding of is the large scale speeds. And why is that? And that's basically because I think I'll just go back to the slide. Yeah. So in this case, the scales were much smaller. So you need to just wait small times, few months or few years so as to see movement. But on larger scales, it takes much longer time to see, which I'll just explain in a few slides. So just before that, I will just give you two examples of jets that have measured complete velocity profile. So this is jet 187 again, a very well studied jet. So this is a plot of the beta apparent versus the distance from the core. What you see, this is basically with various telescopes probing various resolutions or spatial scales. The speeds are low at small scales. And you can see this drastic increase here, average drastic increase at few hundred parsec scales here. So it goes up to 5, 6, 7 times the speed of light, and it drops down again, as you would expect, because the jet has to terminate at some point of time. So what you see here is something of an acceleration that you have in the jet at few hundred parsecs. That is really interesting because it's much far away from the black hole. And thereafter, the black hole must not have exactly anything to do with it at such larger scales.
So, so in this plot, we are seeing like measurements from three
VLBA, HSC, and GLBA.
HSC. And HSC, that's optical.
Yes.
So you're combining radio and optical measurements to find the beta, velocities.
Not exactly combining. So
not combining, but
putting them in the same plot.
So does that matter? Like if you look the jet in radio versus you look the jet in optical?
Yeah, I mean, ideally, at a specific resolution of the radio, the optical will have a similar structure. So when the resolutions are similar, you might have similar structure, but because of the spectrum, the brightness will be slightly different. But as long as you are sticking to the specific wavelength, so what you are doing here is you're observing the jet in a specific wavelength over time. and you have a speed, that is fine. But ideally, you should not combine, let's say, HS2 observation 2000 with BLA in 2010.
That is of course obvious.
Yeah.
That's fine.
But people
what SC said is concern is about radio is producing a different material
exactly.
and optical is producing a
That's
different
what-
material.
yeah.
No, this slightly different is definitely true. But for example, this knot that you see here, HST1, this is seen in the radio as well. So you have to, of course, be very careful in matching the various wavelengths and seeing what we are tracking exactly. But ideally, what matters is what's the speed in these scales on average.
I see.
What is the average speed that you see on these scales?
And so in the other question, if I'm allowed to
Yes,
ask,
sure.
I think in the previous slide where you were plotting the correlate, yeah, so that one.
Yes.
So that's the mean projected distance from the core, and that's the apparent speed.
Yes. For various different
For
sources.
various different objects, so you can see quasar, real lag,
PC1
radio
already
galaxy,
vaccinated.
and then particular objects, 3C111. So is there anything specific that, I mean, this relation is different for different objects? Is that what you are trying to project?
No, what I'm trying to
in that
just
plot?
say here is that this is, I mean,
The slopes look different for.
yes, exactly, of course. And I think this is also because of a selection effect, you don't have anything here. It's just because far away you might see slow and you might not see very much components far away as well. So this was a plot, I think, in one of their papers, which I felt was relevant because it at least showed a plot of the speed versus the distance.
Correct.
At least for different sources
Okay,
too.
so
But at least the idea is it's a plot of speed versus distance. That's the only thing that was done before all of this.
okay, so what am I supposed to see here? That look, there is a speed versus distance.
Yeah.
Rather than thinking that the speed versus distances are different for.
Yes. So the idea is that,
different bodies.
so the question is that, so probing the speed as a function of distance is also interesting, also important. So that's the essential point which I wanted to get here.
Okay.
That's it. Yeah, you see something really interesting here, and this was not the only source. You see something similar for 3C264. This is again another radio galaxy, which basically, so you have different terminologies for different AGN jets. So
That is what northeast or that cannot be used that is north.
northeast.
So in astrophysical images, east
It's
is
opposite.
on the other side.
Oh, I see.
So because you are seeing, yeah. So our east is basically projected is the mirror image of that.
Sorry.
So it's something similar for 3C264, which is again, so the question is what's happening here. And another case, in this case, it's not as extreme as this, but in this case, you also see a plot of the Centaurus A, another jet. You see a BLB observations in small distances. And you see that seems like the speeds at larger scales are higher, but this is not very clear. But the idea is that studies like this will allow us to give a picture of how the bulk coherence factor evolves as a function of distance, which is z from the black hole along the jet away from the black hole. The first question, how does the velocity field evolve as a function of distance along the jet, but how does gamma of z look like? So to do that, as I think I've mentioned a few times before, to do that, you need to measure the speeds of these jets much far away from the black hole, or basically kiloparsec scales or a few hundred parsec scales, not probed by the Mojave project before. So the goal here is to basically make a catalog of motions in jets from HDM using a very large array. So this is a radio telescope. I'll just talk about it in the next few slides. So this is a large radio telescope in New Mexico. So the idea is that it does not have as good a resolution as the very large baseline interferometry technique. So it measures or sees the jet at few hundred to kiloparsec scale jets, basically at nearby ones, like redshifts of less than 0.1. So the idea is that if you have the kinematic study of many jets using this specific telescope, so what you must see is that the speeds, how the speeds change as a function of distance. So the plot here, the figure here, I'll just explain in a moment. So this is an example of a jet, and this is 315. So this is a kiloparsec scale jet observed with the VLA. So if you look at the very large array archive here, so it operates from 1982, 83 until now. So this is a bit of an old picture. So the idea is that at various frequencies, you have all of these observations which are very dense, at least in 10 and 5. So larger circles basically imply more sensitive observations. So you have basically observed for a larger amount of time. So the idea is that So now if you choose a frequency, and you basically choose the jet, choose the frequency, and you go through the VLA archive, and see and identify those knots and see how they have changed their position over time, just like how it was done for the VLBA or the Mojave, for example. And then you have an understanding of the speed. This is again showing you basically a condensed version of this plot for various other sources, showing how rich it is. Now coming to the difficulty of doing this study. So let's start with the first target, as in what is the jet that we wish to first study, so as to see that how its velocity is evolving as a function of time, and also solve questions related to its emission properties. So this jet was chosen because of multivalent observations. It also had an optical jet and various other things, but I'll not go into why this was chosen. But let's say we have a radio galaxy 378, which has a jet. Now comparing this with the VLBI jets, which is basically done with the Mojave. So if you look at this plot here, so this is a jet of very famous pleasure, 30279. So you see y-axis here, y-axis is the time, and you have distance moved as a function of time here. So in 1991, 1992, you see this blob, basically this blob of light here at some 40 light years. If you go to 1998, it has gone to 80. So you can just simply use a scale and just basically a ruler and just divide and just get the speed directly from there and basically do the conversion between arc seconds and parsecs. So in this case, the speed is around 20 times the speed of light. You didn't need to use any technique. You could just look at it and say the speed, and nothing else is needed. But if you look at the larger scales, these are just the small scales, 100 light years or so. If you look at larger scale of jets like 378, where this is basically 200 parsecs. So this much is 200 parsecs or so. So this entire jet is around 1 kiloparsecs in projected distance. And what we obtained from the VLA archive are data from 1985 to 2019, which spans around 35 years in time baseline. So even if you go through 35 years, you see these two knots. So you see these two knots. So this is let's say the core that is stationary, which is not moving, the unresolved core. So this has all of the smaller jets basically unresolved into one. And you can identify these two knots, which are basically A and B. So this is a contour plot with some flux levels, of course. The idea is to identify how these knots are moving as a function of time over 35 years. So you have a distance and you can divide by the time. But in this case, if you just use your eye, you barely see any movement at all. And that is possible because jets in these scales might be much slower, might have much slower speeds than your VLBI counterparts. So in that case, if you have slower speeds, and then they have to move a much larger distance so as to see anything clearly. So you need much more accuracy. This basically has to do with the fact that anything that is moving close to you in a direction perpendicular to your line of sight, like say it's moving from here to here. If the same thing is put away 1 kilometer far away from you, the small movement will not basically catch your eye. It needs to move a much larger distance, which will take much longer time. Which is basically what we see here. You need to observe for much longer periods of time so as to see enough movement. And if the jet is slow here, it's even more difficult. So if the speed here is much higher than the speed far away, which will make it even more difficult to observe stuff like this. So you need better techniques. So you need higher accuracies and more robust methods. So now how do you measure this? So from the image here, it seems that you can't do much. So how do you go about doing this? So you can do it using different techniques. So I'll just quickly give an extremely short summary of how radio interferometry works. So radio interferometer or a telescope measures the Fourier transform of the actual source structure to a certain degree of approximation. So if you just look at this equation here, so this is your sky brightness distribution, which is basically, let's say, your 2D, let's say it's a 2D Gaussian on the sky. You can just, it's a peak and it goes and it basically decreases away from the center. So what the radio telescope measures is something called the complex visibility, which is the Fourier transform of this corresponding sky brightness distribution. So this is the very large array. And these UV coordinates are coordinates of this telescope on Earth. So LM are the coordinates of the source, basically your vectors directing to your source in the sky. And this one here is basically the coordinates of your baseline here. And this is just a basic understanding of how to radio dishes working here. And you have a path difference and you have a phase difference here. And that's where you get the space factor here. So each UV pair is sampled by one pair of antennas, which basically means a baseline. So let's say these two sample 1 point, these two sample 1 point at specific points of time. So the idea is, as you can understand, so larger the distance between two antennas, let's say you are measuring something with these two antennas here, which are much, much farther away. Not these nearby ones, but farther, far and far away. Since it's a Fourier transform, observations using these two antennas will probe the smaller scale structure in your sky, which basically is the idea of Fourier transform. So if you use these two antennas here, these two radio dishes here, it will probe the large scale structure. So the idea is that these two will give you the largest scale that you can probe, and these two will give you the smallest scale that you can probe. That gives you a range of length scales that you can probe for this specific jet. And that's how the radio telescopes work. And this is just a picture of the VLA. The best resolution is given by lambda by B max, which is the effective size of the entire telescope, which is the baseline. And then when you have this, so this is what is observed. This is the raw data. When you have this, you produce the image by deconvolving this. Basically, take an inverse Fourier transform. That is not trivial, and that's the basis of how radio astronomy works, and it takes a lot of time to do it. Now, coming to our technique. So as I mentioned before, that you need very highly accurate methods to measure that. So now you can understand that if you have something that requires extremely highly accurate methods, and you're taking a Fourier transform of that, inverse Fourier transform of that, it already create some problems here because it's not the raw data exactly that you are probing. So what is done here is that I'll just quickly show it again. So this is not a continuous plane, right? So when I say mu v is the coordinates of this telescope array here, this is not continuous. You have holes here. So it basically is that you will not be able to sample your entire reciprocal space, which is given by this u v here. So that will create some non-uniqueness in your inverse Fourier transform. I can talk about that if you are interested later on. So the interferometer observes this quantity here, which is the complex visibility. These are the error terms, gain terms versus the true visibility. What we want to do is we want to measure this by removing those factors there or by calibrating. So this is just an example of what a radio telescope does. So on the right, you have the brightness distribution. If it is a point source in your 2D point source in your XY plane, you take a Fourier transform, you get the amplitude and phase. Same for an extended source, goes down. Same for a bilobe source here. You have this ringing of oscillation. So the idea is that what you want to do is that you model, instead of modeling the image, what you're observing, you model the Fourier transform, because that is exactly what you're observing. So the optical telescopes, X-ray telescope directly measure your image on a charge coupled device or a CCD. So that's the raw data we have. In this case, the raw data is this. So the best method to have highly accurate results is just to hit the object, basically hit the telescope, hit the observation where it's basically directly measuring the signal. In this case, it's basically the Fourier transform. So this is what you observe. So what you want to do is have a model of that and then see how it changes in time. All right. Okay, I won't discuss this much. It's just basically something of a different kind of a new software which required modifications to do that. So I'll just go to my results after this. Yeah. So the idea is that you needed to develop a bit of new software, change previous software so as to do this kind of measurement, because you require much higher accuracy. So I would say the takeaway is essentially that to do better or more accurate observations of jets on larger scales, as in how the structures are changing in time. So what you do is you take a Gaussian and take a Fourier transform of that, and then see how the position of the Gaussian is changing over time. That's more accurate than just modeling the image, because the image can have errors. So now our techniques are developed. What results do we get? Coming to the physics directly. So coming back to target 1. So I'll just speak about this plot, then talk about this for just 1 minute. So if we just look at the data points, nothing else, absolutely nothing else. So this is the bulk Lorentz factor. You can see it's pretty slow. It's not pretty fast at all. And this is the deprojected distance along the jet. When I say deprojected, that basically means that since you're observing the jet at an angle, the distance that you see is the projected distance. The actual distance in reality is this distance, right? My hand here. So basically divide by the cosine of that angle so as to get that deprojected distance. So this is the plot of gamma versus the dipolate distance. So you have 3 points, 1, 2, and 3. So this was from the Mojave observations, the VLBI, which is basically few parsecs. These two are the knots that I showed you before, A and B, that was at a few hundred parsecs. So what you see is the speeds at these scales are larger than the speed at the smaller scales. What can this imply? This can imply two things. The first thing is the jet accelerated very fast somewhere here. Then now it is in a deceleration phase. So these are 2 points. 2 points don't necessarily tell you that this is indeed increasing here. This can just be that there is some fluctuation here. But the idea is that this is larger than this. That's the essential idea here. So that is one scenario. The other scenario is the jet has been continually accelerating through these distances from few parsecs to hundreds of parsecs. And what these lines here tell you is basically something called thermal acceleration, which has to do with two things. The first thing is if you have a supersonic jet, so I think you have learned in fluid mechanics that fluid dynamics that if it's a subsonic flow, the area and the velocity go inverse of each other. So if you reduce the size, the velocity increases, but if you expand, the velocity goes down. And exactly opposite happens if you have a subsonic flow. This is the equation that governs that. So basically 1 minus Mach number squared is basically the speed of sound by the velocity here. If this is less than 1, you see that the signs on both sides of the equation are the same. So this is something called a de-level nozzle. So it's a specifically designed kind of system in which you have very specific boundary conditions. So what happens is you have a converging subsonic flow, increasing speed here, and then you have a diverging supersonic flow here, and then it keeps on increasing. So the idea is that as the jet expands, the speeds increase. And that's what happens here. So the idea is that what causes this acceleration? What's happening in as far as the energy goes? So internal random motion of the molecules, internal energy of the jet, not molecules, sorry, particles, is converted into directed kinetic energy by continual expansion. And that's exactly what these models tell us here. So when I say an adiabatic jet, there is no energy injection after the jet has left the black hole. So and this parameter here basically tells you the ratio of the internal energy to the total rest mass. So basically when you have larger value of zeta here, which implies that you have larger initial energy, and what you see is for 0.17, the jet reaches a much higher speed, not much higher, but higher speed, slightly higher speed than the one which is in below here. And all of these are consistent with this. And when I say quasi-isothermal, it's not exactly isothermal, but there is specific prescription where you keep injecting energy, so it keeps on increasing. But the idea is that this is just a very basic attempt at understanding what's happening. The conclusion is that jets indeed accelerate at the larger scales, and most likely it is something to do with the thermal acceleration. There are other theories of acceleration too, which includes magnetic acceleration, but I won't talk about that today. I'll quickly, I don't have much, I think I'll start quickly wrapping up. This is another target that we observed. This is something very different from the previous case. This is a much faster jet. So we had more observations, but I just want to show you 3 of them. 1988, 1994, 2007. So this is a core subtracted image, which basically means that the bright part has been removed from the image so that you only observe the jet, because you are not exactly interested in the bright part. The contours give you where the bright part initially was. We removed it. So what you see is just the remaining part of the jet. So when you look at this bright spot here, and you just draw a straight line, it has moved. It has moved this much distance, and this much distance on the screen here is a lot of distance when you basically mean when it's a kiloparsec scale jet. It's already, I think, tens of parsecs already, even more than that maybe. So now if this is moving really fast, what is the speed? We find the speed is again close to 10 times the speed of light. That is a longitudinal speed here. And from there, we can have an idea of what the bulk range factors might be, and as well as the viewing angle from this. Yeah, so this is another example where we have a jet that is extremely fast, just like M87, 3C264. And this is really interesting, and we are trying to understand what exactly caused the acceleration here. I have five more. 10 minutes. Okay. Yeah, this is just my first conclusion. This is the first observational evidence of possible thermal acceleration in an extragalactic jet. Again, just to not be confusing. So when I say extragalactic, it basically means jets from galaxies which are not our Milky Way, outside our galaxy. So again, another example possibly. So we need to understand what's actually going on. So these two are the first two targets that was put in basically for this catalog. It's basically, so I think newer people are working on it. So it intends to be the benchmark for kinetic theory and large-scale jet spectra. I'll just talk about this in a moment. How do you do it? Yeah, and so okay, all right. So I'll just quickly go over the second question. How can our results aid in understanding jet emission mechanisms? As I mentioned, I think towards the beginning of my talk, you have multiple questions. Jet acceleration, jet emission, and the structure of the jet. What do the knots mean and what the jet is actually made of? The first question is, why do kiloparsec scale radio jets produce X-rays? I will not go over this. I don't have the time, but I'll just test a few words here. Yeah. So this is an observation of a jet this is basically another object called Pictor A. It's a very large, it's almost tens of kiloparsecs here. So you have, this is an X-ray image. X-ray image basically in KEVs, which we observe the Chandra, soft X-rays. So you have the core here, you have multiple knots, and you see something like a so-called hotspot, which is where the jet turbines. So this is in the X-rays. The question of how exactly, in many cases, not all, but is that how are these jets energetic enough to produce high energy emission? It can be various things. So, and it's done on a case-by-case basis. So the observation is this, the theory can be multiple. So it can be something like inverse quantum scattering of CMB cosmic microwave background photons. So when I said inverse Compton, I mean, so you have synchrotron radiation, inverse Compton radiation, where high energy electrons upscatter or increase the energy of incoming photons into higher energy photons. CMB is in the radio, or maybe depends on the redshift, of course, what the CMB would be. Synchrotron, okay. If the electrons are highly energetic, any seed photon field, which can be or anything other than a CMB, and different types of modeling processes, modeling techniques, which can be one zone, multi-zone, as in stuff like that. Yeah, this is again another jet, which is 3C273. So the question is, all of these, part of this theory involves the speed of the jet. That's why we are interested in this. So basically, if you have the speed of the jet measured perfectly, you should be able to constrain what's going on here. And this is just an example here. For example, the gamma mean of this jet, which is basically kiloparsec scale jet, was determined to be less than 3, which is not fast enough for a specific type of emission mechanism. This is a lot of detailed slide. I just want you to focus on just this part here. I'll just talk about 10% of what's going on here. So this is a plot of a spectrum of a jet. I think it's important you see that, because so when I say plot of a spectrum of a jet, so the jet, as we saw before, you have the core and you have the large scale extended jet. So when you want the spectrum, you need to choose where you want the spectrum from. You can take the core, that is basically these gray points here, much brighter gray points here, and goes on here. So this part is unresolved. You don't have good resolution telescopes. So what you have is a range around 10 decades in energy, which goes on 10 to the power 8, 9 gigahertz, 10 to the power 27, which is almost 15 orders of magnitude in wavelength, and that is fantastic, and that's pretty broad. So the same source is emitting in all of these wavelengths, and so this is true for many jets. So this part is the core, this part here. When you see these red points here, so those are data points from the jet, which are not basically the core. So then the idea is that, can you model this with your usual spectrum, with your spectral modeling and things like that? So this was an attempt to do that with various models. And just to tell you, you see these two humps. So you see these two humps. So this hump is basically mostly due to synchrotron radiation, and the higher energy hump is due to inverse Compton. That is generally true, but in many cases it may not be. And you might ask, why do you have this hump? This hump is basically because of this multiplication of nu times f nu. So in a usual spectrum, you just see flux versus the frequency. In this case, which basically should be, let's say your flux versus frequency is this. It should become like this, and like this, which basically is two breaks in your frequency, in your flux. So you multiply that with the frequency, and then you basically get something like a hump.
So even in observation, in optical, you can resolve the central part and jet
With HST. Yes. And nearby.
Few sources.
Nearby jets. Very nearby jets. Yeah. And few sources. This is another example of spectral modeling, but in this case as well, we had to use different types of models to understand what's going on. But the takeaway is that the speed of the jet is extremely important. It determines the relativistic beaming, which basically will tell you the observed flux level, because the flux levels are extremely sensitive to your speed of the jet, which goes in your Doppler factor that I mentioned before, gamma times 1 minus beta cos theta inverse. And coming to the other part here, that is about the knots. So this is basically mostly my last slide before I just talk about my conclusions. So the idea is that this is let's say this is an example of a jet, Cygnus A. You observe the jet through various resolutions and you see various scales. So what you observe, this I think I showed this towards the beginning of my talk. Beta apparent is the speed, which is given by beta sine theta minus 1 minus beta cos theta. So when I say beta pattern here, this is just the speed of this pattern or the compact source of light that you see. That might not directly reflect the speed of the jet itself. Because the beta pattern, let's say so these patterns or knots can be understood as shocks, which are basically shock waves that are extremely fast and they have energized electrons and they are moving at some speed. So this will basically reflect the speed of the shock that is moving in the jet, not the speed of the unshocked jet or the unshocked fluid. And that is basically simple Lorentz velocity addition. So this speed of the shock will be given as Lorentz velocity addition of the speed of the jet with respect unshocked fluid with respect to the shock, plus the speed of the shock in the frame of the jet. And basically addition of that, and therefore you get this. The speed we are actually after is this speed, beta pre, which is the speed of the pre-shock fluid or the speed of the jet, actual speed of the jet. And in most cases, this is not a problem because the jets are extremely fast, highly relativistic, and in most cases, these are very similar. But for low speeds, when I talk about low speeds, basically means speeds in the larger scales or kiloparsec scales. We need to be very careful in equating the shock speed and the jet speed because that will give you very different results. All right, so just coming to my concluding remarks. So large-scale jets are a mystery. I can talk about it for more time if you're interested after the talk. These are very, very specific ideas, and if you're interested, I can talk about them as well. So the takeaway is that large-scale jets are a mystery, and we are still trying to understand what's happening. And this time is right because the very large array has a large time baseline. So with that, we can observe these jets and their dynamics currently. And if we have an understanding of the bulk Lorentz factor, we should at least reduce some of the uncertainties regarding these large-scale jets and their emission processes. All right, just to finally end with this. So just a bit of what I learned over the last 6-7 years about doing jet science. So how do you do jet science with minimal bias? So you'll never have the perfect telescope. You'll never have everything perfect. You'll never have all your proposals accepted. You'll not have time in all telescopes. So, but given archives, so you have archives that are extremely dense and extremely rich. So ideally, you must use archives and your proposals. Using maximum observations available at present, there will never be all perfect telescopes through all wavelengths. So that's all you have. You have to do everything with that. Specifically for jets, ideally there should be attempts to tie discrete sets of observation and theory together. So the problem is that people working in this jet launching region, M87 black hole shadow, they are working basically with the observations with the Event Horizon Telescope people and people who are doing just hardcore simulations. They are talking amongst each other, but no one is talking. So these people are not talking to them and these people are not talking to them. So, and in this case, it's a different field altogether, different subgroup in astrophysics where you have large scale proper motions, large scale spectrum structure and different things. And the other thing would be, which I have not worked out because that's why I didn't put it here, is that about the termination part. So you have launching, transport, and termination. So for termination, it's again a different subgroup. So all of these groups are not always talking amongst each other, which should be done. And finally, I guess this is exactly what I was trying to tell you. So towards a complete picture by linking physics from the event horizon scales to kiloparsecs by filling in the gaps with studies like canons. And coming to my final slide. Takeaways if you had zoned out at any point of time. Extragalactic jets accelerate to hundreds of parsecs. The mechanisms are various and they can be tested if we have full observations of velocity profiles from small to large scales. Large scale jets are a mystery as far as the emission and dynamics are concerned. And finally, this again, more of a personal opinion. So devising exact ways to connecting observation and simulation should be worked through. It's not possible without mixing of observational theorists and theoretical observationalists, which basically means that you're a person doing theory all the time, person doing observation all the time. If you are talking to each other, that's not enough. So the person doing theory must know observation, and person doing observation must also know a bit of theory. And only after mixing of these two kinds of groups of people, we should have something. Otherwise, I think we are not doing much, I would say. With that, I come to the end of my talk. I will take questions.
Okay, questions? Yes, somebody.
How the theta is measured?
Theta is measured. Okay, so there are various ways you can do it. So one way is this, for example. So it's difficult to measure theta. So if you just have this, you can have a lower bound on gamma and the maximum upper bound on theta. But those are just bounds, not exact values. But if you also have a measurement of the jet counter jet ratio, which is in this case here, you will just have a limit because you don't see the counter jet. But if you see a jet in which you see both a jet and counter jet, in that case, what you can do is you can find the flux ratio, but that also has its issues. But in general, let's say you have an approximate flux ratio, then you can combine these two equations to eliminate, so to eliminate R and beta apparent, you just get beta and theta from there. That's one way to do it. So that's a good question because there are a lot of uncertainties involved in measuring that as well. So in most cases, we can produce a range between which it must lie, and also with the spectrum as well. So in the spectrum, if you have a specific type of model, you can have an understanding of that. But the problem with that is those are all model dependent. Depending what model you choose, you'll have a different fit to your variable. This is it's also not exactly model independent, but this is much better as a least model dependent method of quantifying speed as well as the beta, as well as the theta. But this is not possible for all jets, so you must proceed with approximations in most cases.
Other questions?
Can you go back to the slide where you have two graphs?
Two graphs, this one?
Yeah. There is one plus there. There is 1 plus Z.
Yes.
Why are we using 1 plus Z? It's a unit shape, right?
Yes.
Why
You
don't
can
we not in 1 plus Z?
This is in log scale.
Yeah.
So if you start with
So no, the question is also that instead of Z.
okay, I
why
see.
1 plus Z?
So this is what comes up in everything because this is basically with which you are. So let's say that's a random example, like the CMB energy density is boosted by 1 plus Z to the power 4. And also I think in all of the cosmological equations, it is always mostly a function of 1 plus Z. So it's just to, I think, keep that
So
convention.
this is actually 1 plus Z, 1 by 1 plus Z.
Yeah.
Find just something called the
Scale
expansion.
hai.
It is assumed that at Z equal to 0,
British
we
amala
can
kore.
write that
Wait,
A
which-
equal to 1. That's why the 1 plus
Wait,
Z is done.
Oh, that is scale, right? Yes.
It's one inverse of the scale.
Yes.
As you normalize.
Yes.
Other questions? Okay, SSF.
Okay, first question is, so with your new improved technique to measure the.
Yes.
No,
Yes.
you are beating even the actual resolution of lambda by D or?
No, it is not about exactly beating the resolution. It is almost about so.
So you see like something is moving from here to here. That's is my goal. Simple goal is that.
Yes, you can't see it with this picture here. The first thing is
No, I can't see it.
you can't see it here. So you need to deconvolve it.
No, but even that's
Yes,
what I'm saying.
With dynamics, you always beat resolution. Right?
Yes. I
If
mean,
you
what I'm
have
saying is
motion,
that deconvolve it and
by
just
blocking one motion and blocking the other motion, if the blue shift, red shift, that's telling you whenever you are doing spectroscopic
so
things,
yeah.
you are beating the resolution.
So in this case, you don't see the 2 knots, but this is basically because of resolution. So I deconvolve it, I'll see the 2 knots here.
Diffraction limit.
Yes.
I'll just see the 2. I mean, in the Fourier space.
That's the whole idea of the
Yeah. So we are beating basically if two things are lying within each other's beams, which you can't do here, which you are just deconvolving and getting them separately. So that way you are beating resolution. Yes.
Okay, I think so. Mine was like two simple questions. The one is the last one when we're talking about beta shock and beta pre-shock.
Yes.
So as you say that for lower speed jets, this is more of an issue. Is that right? Am I right?
Yes. Well, lower speeds, I mean, let's say gamma less than 2, less than equal to 2.
For gamma less than 2, this is an
Yeah.
issue. What is the order of magnitude? Like, I mean, how much error am I going to make if I don't take into consideration this thing? By
No.
ACD, you mean spectral energy distribution?
That is also, yeah. So I think I have not, but I can give you an example on that. So it is possible that, let's say, your speed here is non-relativistic. This speed is non-relativistic, but this speed has become much higher. They are not exactly independent. They can be equated by some boundary conditions.
You
But
mean after the shock, it has become relativistic? Am I?
no, what I'm saying is you have a fluid which is not very relativistic, but a shock is traveling much faster than the speed of basically the liquid itself.
Yes.
That can give you something which is very high, but that is not tracing the speed of the fluid. Yeah. But it depends specifically on the shock boundary conditions and everything, all of that, and densities and all of that there. So my primary point is that certain things need to be just checked before doing that. Yeah, that's all.
And
I have not worked further on this. Yeah, so yeah.
And the second question, I'm just curious. Is SK going to do any good thing with jets?
With observations of jets, of course, I mean, we might have better sensitivity and better resolutions, but just for specific observations, it might be doing good. But as far as my work goes, because it will at least provide a larger time baseline. So we are studying for 1980s. And if we have SK 2030, 2040, its goodness won't exactly be because of its facilities, but because it's a new telescope observing later in time.
Time.
Yeah, because of time. Yeah. So if SK was built before, it would be good. I mean, better than the VLA because it's better that way, might be better. But building it now is basically important because we are just moving forward in time. If we have 5 more years, it's also always goes.
Also, SK is, what is do you know the frequency range? Because I thought it is more of a lower frequency.
Yes, lower frequency as well.
Don't move from this. I have a quick question from this slide. So, if the beta pre is 0, then beta shock is beta pattern is beta shock.
Yes.
So my question is, I mean, is the beta pre, I mean, is that something that
So beta pre can't be 0, right? Because the jet has to move.
Yeah, but you don't know. So that's my question. That I mean, as I'm learning that I have become sort of backdated. So I'm asking you to update me that I mean, when we say the shock is moving, do we really say anything other than the knots that are moving? I mean, it's not clear whether.
No, yeah,
maybe the shock is just knots.
Yes. So the thing is, when we say the knot or the shock is moving, what we are tracing is the energized particles just behind the shock. The speed of those particles, that's what we are
I
tracing.
am saying that you are saying that, okay, this is a knot and this is moving away.
Yes.
And this blue part probably, let's say you are saying roughly that is the ambient jet.
Okay, yes.
My question is, if there is no ambient jet, maybe what we call jet is just bunch of knots moving and there is nothing.
That is possible.
Is there a possibility
That depends on the scales as well. So